Good morning, students. Am I audible? Hello, students. Am I audible? Hello, am I audible?
Yes, sir, you are audible.
Thank you. Okay. So we developed the. Let me continue. We developed the equivalent circuit of an induction machine circuit model, which is very simple, and some of you may note that it more or less looks like a transformer. Uh, However, unlike transformer, it doesn't have as such any electrical output port, because machine is such a thing that doesn't require an electrical output port. Transformer requires electrical output port, because transformer electrical power is input, and after isolation the same amount of electric power in an ideal transformer should be the output. Whereas in an induction machine, the objective is to produce torque. So therefore electrical power is input and mechanical power is output. Therefore, if you remember the equivalent circuit, this part, this is R2 by S into 1 minus S represents the mechanical power output with an equivalent electrical resistance. And this electrical resistance is function of the rotor resistance and the slip of the machine. S is the slip of the machine, and you know the definition of the slip. Slip is omega S minus P by 2 omega rotor by omega S. We defined omega S as the stator supply frequency in radian per second, omega rotor as the mechanical speed of the rotor. We had defined omega R as the frequency of the voltage or current in the rotor coil, and we had defined omega synchronous, that is the synchronous speed of the magnetic field, the speed of the magnetic field in radian per second. So you have seen the physical meaning of this. This is the port R2 by S into 1 minus S. This one we are identified as the port through which mechanical power is output, but electrically it looks like short. Electrically it looks like as if there is no electrical power output. It is true, there is no electrical power output, but this equivalent circuit takes care of the power balance. Power balance is taken care of. Power balance means electrical power is input and mechanical power is an output. And this mechanical power output is represented in this electrical equivalent circuit in terms of rotor resistance and the slip of the machine. Slip of the machine contains all the information of the mechanical speed of the machine, right? Otherwise, you know the physical meaning of the components. R is the stator, R1 is the stator resistance, JX1 is the stator leakage inductance, JX2 is the rotor leakage inductance, R2 is the physical resistance of the rotor. This dash term implies that they are all referred to the stator side. JXM represents the magnetizing inductance of the machine, and XM is related to the current that will be required to develop the magnetic field in the air gap. So that current is Im, and you may note that, if some of you may remember, that magnetizing current is also a part of the equivalent circuit of the transformer, but the magnetizing current of induction machine is greater than magnetizing current for the same kind of voltage of the transformer. And reason is simple. In a transformer, there is no air gap, so therefore very little current is required to develop the magnetic field, because the flux lines are always passing through the magnetic material, namely the iron. Whereas in induction machine, the flux path contains a portion through the magnetic circuit and a portion through the air gap. The equivalent circuit may look like this: R iron, reluctance of iron, and reluctance of air gap. And this is the MMF. This is the flux. This is the flux air gap. Flux air gap or flux in air gap in the case of induction machine. Since flux is related to flux density and cross-section area, in order to develop the same amount of flux, we need more MMF. This is the MMF. This is the more MMF. We need more MMF in an induction machine because it has higher reluctance. We need to develop the same amount of flux. It has air gap. In the air gap, I have to develop the flux level. So we need more voltage. As if it is a voltage, flux is current, and reluctance is like resistance. If you know, if current has to be same in a circuit with higher resistance, then you need higher voltage. So that is this MMF, which is being represented by magnetizing current Im, and this magnetizing current will be more because the reluctance of the induction machine due to its air gap is more compared to the transformer. Okay.
Sir?
Yes.
In the equivalent circuit, should the direction of I2 not be opposite?
Yes, you are right. Correct. You should be opposite. Acha, but can I make a commonsensical change from now on? What I am saying is that actual direction of the current or the power wise, power is going in and power in here and power output here. So what I am saying is that this, if you want, I need to name, then I will write it as IL. Is that okay? Will that be okay? I2 dash is equal to minus IL. I just want to keep from now onwards a commonsensical feel of it. The commonsensical feel is that current and power is going here to the load. Amitabh, can I do that? Can I?
Sir,
Yes, sir.
means direction should be reverse. I didn't understand. Can you explain that?
No, direction is as per our convention of development. We took the coils like this. Stator coil current is like this. Rotor current is like this. They combine together, create the magnetic field. That was the direction in our derivation. You look at that. So that's why he's saying there. I said that this is stator. I used a current stator. I used a current rotor. Okay. Now, or you may say that I am now using I2 dash as the variable. So I will say I2 dash is equal to minus IR, or I will say I2 dash. Amitabh, just I am changing a convention, nothing else. I am defining, you had defined earlier all equations, the rotor current direction is towards the coil. That was the direction, and stator as towards the coil, because we wanted the symmetry. the symmetry of the equations we wanted to write. If you remember the way we had written stator equation, exactly identical way we had written the rotor equation. Only thing we had put it to be 0. So to make it symmetric, we had chosen stator current direction in dot convention, stator current, rotor current direction in as the positive direction and rewrote the equations. Now, just to make sense in the common sense, just to aid our common sense, now I am defining I2 dash is equal to minus IR and putting the arrow here. That is same equivalent. I am putting arrow direction is equal to that. So it is basically the same thing, right? Instead of writing IM, earlier we used to write what? IM is equal to IS plus IR dash. We used to write that. Now I will write it is equal to IS minus I2 dash. That's the difference. No other difference. Is that making sense
Yes,
to
yes.
you?
Yes, understood.
It's just a common sense. Just a sense.
Sir?
Yeah, please.
So in the equivalent circuit, shouldn't it be R2 dash upon S into 1 minus S?
R2 dash by
The
S.
mechanical power output.
Yes, sir, it will be R2
R2
dash.
Yeah, R2 dash. I am sometimes putting that R2 dash part I am forgetting. Yeah, please be careful and R2 dash. So you also again know after some time one may say, let us know why to put all the time dash dash dash. In our mind we understand that it is existing and let us write x2, r2 and r2 1 by s by s. Sometimes and I2. They said I have done one more adjustment of the variables where I know that every quantity is with respect to the stator reference frame, with respect to the stator number of turns, but by writing again and again variables is a little bit cumbersome, but not a bad practice. I myself most of the time write dash because just to remind myself that these are all not physical R2 but actually R2 adjusted with respect to the trans ratio, and that's what I want to remind again and again. But so I write it. But many books and many places will see that one line they will say in the beginning, the all quantities are with respect to the stator. All quantities, they will say one line. After that, they will freely use x1, x2, r2 like that. Well, all quantities are with respect to the stator thing. So after that there is they can afford to use R2 instead of R2 dash. But you write, and there is no that is a good practice. Okay, so basically, if you look at this, one more thing I want to tell you that a little bit physical feel of what is happening is, if you look at it, just take a very simple, ordinary look at this circuit. After all, it is now it has become an electrical circuit. So all the physical meaning should have thing. So the power that is entering from stator, this type is stator. So power in terms of what is the power that is entering, if I call it PS. So PS is the stator power. Do you understand that the power that is entering from the stator is now can be expressed by our phasor relationship between supply voltage Vs or the stator voltage Vs, that is also the supply voltage Vs, and the stator current I1, and the phasor relationship between them. That means Vs, Is, I1 cosine of the angle between Vs and I1, right? That would be the power that is going in. Then what happens? Let us trace the power path. Then what happens is, next thing what is happening is some power is lost in the stator resistance. It is small amount of resistance. We never want the stator resistance to be very large, and so but it is there. In case of we're doing the accounting of the power, we have to take care of that also. So R1 some loss is there. After this loss is taken out, that means whatever stator power has entered minus this stator copper loss, we'll call it copper loss. What is that power? There is a specific name to that power. That power is called air gap power. That means that is the power which is jumping the air gap and entering the rotor. It is now not in the physical stator, but power had entered through stator coil. But now it has jumped to the machine's air gap and going to the rotor portion. So this is what is known as the air gap power, right? And that is defined as PG. So there is a name to it. They call it PG or air gap power. That is power transferred across the air gap from the stator. Okay, which is nothing but, as we know, it is P stator minus I1 square into R1. By the way, you must understand that this is a single phase equivalent circuit. In a three-phase machine, everything is 3 times that. You must understand that. So even if I forget sometimes to write 3, I am telling in the beginning itself, since it is the 3-phase machine, actual power will be 3 times whatever the single phase equivalent circuit indicate. Okay, actual power, actual torque. Only from this you will know what is the per phase current and per phase voltage. That is what you will know. But power and torque you have to multiply by 3 times. Right. So this is the stator power, and the stator power is equal to how much? This air gap power is equal to how much? So let us look at this circuit again. And what do I see? What is this power equal to? This power, obviously no power loss happens in the inductances. So JX1 is not, there is no power loss. So that's why you said PS minus I1 square into R1 is the power PG. Now this PG power, if you look at it, XM also not contributing to any power, active power, right? And similarly, in the rotor side, JX2 is also not contributing to any active power. So all the power PG must be spent in this combination, in the combination of so-called 2 things. One is the rotor resistance, and another is the is an equivalent resistance that represents the mechanical power output. So put together, these 2 resistance is nothing but, put together this resistance is how much? R2 dash by plus R2 dash by S into 1 minus S. Put together, if I sum them together, it is equal to R2 dash by S. So air gap power must be related to the power that is spent in R2 dash by S. This is metaphorical, right? This is as such, this resistance doesn't exist. The physical resistance that exists is the existence of the rotor resistance R2 dash. But from the power point of view, in order to ensure that power balance is maintained, we are thinking there is a metaphorical resistance R2 dash by S exists. That is a slip. That is the consequence of the mechanical output of the system. A slip part comes, and you see the slip is less than, very close to 0. It is definitely a fraction. So R2 dash by S is greater than R2 always. R2 dash, not always, I will say, is greater than R2 dash. So on most of the conditions is that because slip we don't want to be high. Slip is very close, 0.2. It is 0.02, 0.03, 0.04. This kind of numbers we expect, at least during running condition. Under when it has after acceleration, it has reached the steady positions and delivering the rated torque, we expect the slip to be around 2%, 3%, 4%. So this number wise it is higher, and your common sense should also say that it has to be higher, because otherwise how do I account for the mechanical power that is going out? That is mechanical that is going out, because the power that is entering the air gap, if it is entirely spent on the rotor resistance, that doesn't make any sense. Rotor resistance should take only very little power out of that. Whatever power is entering through the air gap, only take a little bit of it. The most of the power that is entering through the air gap should go through the as an output through the mechanical as an output as a mechanical power output, right? So therefore, PG is equal to, we can say that, let us add another page. Therefore, PG is equal to I2 dash square into R2 dash by S. So therefore, P out is equal to I2 dash square R2 dash by S. I am putting 3 now, just to mean that it is a 3-phase machine. This minus 3 into I2 dash square into R2 dash. So it is equal to 3 into I2 dash square into R2 dash by S into 1 minus. This is the power out, right? Here I should pause a little bit. Here, this power output is slightly internal, because after this there is some loss. Some loss, because it is a mechanical system, it will have some loss of friction, windage, etc. Some mechanical loss will be coming before it goes to the shaft. Shaft means shaft power is the power that is useful by the useful for the mechanical system. So it is still an internal power. Just we have subtracted the rotor copper loss. This corresponds to the rotor copper loss. Just we have subtracted the rotor copper loss. Still it is bit internal. So the it is output, but let me put it as what I say, name internal word I should use. Okay, so P out external would be this P out internal minus other losses. These losses are mostly mechanical losses. Mechanical losses like friction, etc. Friction, etc. This sort of losses will be there. But you must have also noted one interesting thing, that we are not talking about iron loss at all. We talked about copper loss, and iron loss we didn't talk about. It's true that the equivalent circuit that we have developed assuming that there is no iron loss in the machine, and therefore in the equivalent circuit we don't have this branch. You must have seen that we have not put this branch. This branch used to be iron loss. What was to be the R iron? Let me write it that way. At iron loss branch used to be put in the case of transformer. Transformer would used to have this kind of thing. So this we have not put here. Okay, there are few reasons. One reason at least I can give you to put it why this is not put. And the equivalent circuit has been developed with the assumption. We have developed it with the assumption that there is no iron loss. So that makes sense that we are not putting it. It is not appearing in the equivalent circuit because the prior assumption was like that. However, when we want to think about iron loss, is it there or not there in this machine? If you think very carefully, means you have to think in terms of little bit in terms of the field. Iron loss essentially is coming due to the magnetic field fluctuations, the BH curve. You remember the BH curve? That BH curve is cause of this BH curve is the reason why I'm not drawing well, but this BH curve is this one side is H, another side is B, and this area is every time there is a flux excursion, every time this amount of loss is happening in the machine, and so as the frequency is there, it's a function of the frequency. The higher the frequency, the higher will be the loss. So here comes the clue. Is the frequency, what is the frequency of flux excursion in an induction machine. Okay, rotor is rotating, stator is stationary. So rotor is rotating very close to the synchronous speed. Synchronous speed is the speed at which flux excursions are happening. The flux is changing from north pole to south pole, north pole to south pole, south pole to north pole, like that. That change is occurring because the magnetic field is rotating, and the stator magnet is stator iron is stationary. So through the stator iron, you will see north pole, south pole excursions going on at the same rate as the synchronous speed of the magnetic field. So there will be a stator iron loss, because the moment there is a change in the magnetic field polarity in any magnet, then there will be iron loss, because magnetic field is then accordingly always changing. Positive, negative, they have to change, and according to the flux density, positive, negative, they have to change, but they don't go through the same path, and therefore there is a loss trapped in the iron part of the thing. However, stator has iron loss. Stator. So we conclude that stator has iron loss. However, rotor doesn't have much iron loss. Doesn't have much iron loss. The reason is the same, because the rotor speed is almost equal to the speed of the synchronously rotating magnetic field. So with respect to the rotor, magnetic field is rotating very, very slowly, right? Rotor speed, for example, if the slip is, let us say, 2%. Suppose it is a 50 Hz 4-pole machine. 50 Hz 4-pole machine means it is 1500 RPM is the speed of rotation of the magnetic field. And this will be 98%, 2% is 30 less. So the rotor is rotating at 1470 RPM. 2% I have reduced. So it is 1470 RPM. So the difference is only 30 RPM. So with respect, if you are sitting at the rotor, you will see that the magnetic field is changing very, very slowly, 30 revolutions per minute. So we, for all practical purposes, we sometimes, we most of the time ignore the iron loss in the rotor. Obviously, there is a starting phase and reaching phase, but we ignore it. Most of the analysis that I'm talking about is talking about the analysis that is done under steady state. Okay, we are learning the how it starts and etc. But our most of the focus is on the steady state analysis. So this is the thing that happens, right? So this is iron loss we will be ignoring, and but the mechanical, if somebody says you take care of the iron loss, you will subtract it at this stage. That means first you find out P out internal, then you find out what is the mechanical loss given. This data will be given to you. You don't have to do anything. And the iron loss part you have to subtract at the end. Don't argue with me, sir, power, air gap power here, there, all that. Don't argue. These are all engineering is somewhat based on the convenience also, right? So they have, it won't make much of a difference in the analysis. So they have as if shifted the loss corresponding to at the end. This iron loss that is happening in the air gap is shifted at the end, right? A little with a little error that is coming in this case, right? Now, for simplicity, we are ignoring these two parts, mechanical losses and frictional losses, and trying to find out what is the torque. So P out internal, based on that, if we want to find out torque, so T out we say TE, electromagnetic torque, is equal to P out, yes, by omega mechanical, or P out by, in our definition, it was omega rotor. So P out is equal to 1 minus S. This is equal to 1 minus S PG. So it is equal to 1 minus S PG by 1 minus S omega synchronous. So 1 minus S cancels. So this is equal to, has a very simple expression of PG by omega synchronous, which is equal to 3 into I2 dash square R2 dash by S by omega synchronous. This is the basic expression of the torque. It is very simple. The air gap power, 3 times the air gap. 3 is just for the number of phases of the machine, that is 3, and otherwise it is the air gap power divided by the synchronous speed. Actual torque is P out by the rotor speed. This is the actual torque. But P out is 1 minus S omega S, and omega rotor is 1 minus S synchronous speed. These two cancel. So this becomes PG by omega synchronous. Omega synchronous, not mechanical. This is PG by omega synchronous. Synchronous speed is the speed of rotation of the magnetic field. Omega rotor is the speed of rotation of the rotor, mechanical speed of the rotor. That is omega rotor. That is how we have defined the thing. Okay. So now then our job is just to solve the electrical circuit and find out what is I2 dash square. That is nothing. Now everything should be in the comfortable zone. Whatever you have done in the first year, how do you find out I2 dash, right? When given all the parameters, how to do the I2 dash. Here, sometimes some people make some approximation. I will show you 2-3 things, 1 or 2 things here. Let us say this is the basic equivalent circuit. Let me draw it one more time. I am not breaking it now. I am just drawing one R2 dash by S, JX2 dash, JXM. This is I2 dash. This is I1. This is VS. This is R1. This is JX1. So how to find I2 dash? One of the ways is to make an equivalent circuit, that is, make it equivalent to that is keeping which one unchanged? I1 unchanged. It will solve for I1. By this equivalent circuit, what we are doing is these two things, this thing is equivalent, made equivalent, and these are the equivalent. I name it RF, JXF. So what is RF plus JXF? That is equal to JXM in parallel with R2 dash by S plus JX2 dash. This is one equivalent circuit, and here you will get directly the current I1, and from that subsequently you can get I2 dash. This is one approach. The second approach is mostly used, that is this. That is R1 JX1, and this is the basic circuit it was. Right. So here we will preserve I2 dash. I2 dash we will preserve. So therefore we will do Thevenin equivalent circuit of this. This is VS R1 JX1 I1 is JX2 dash R2 dash by S. This R2 dash by S and this will be preserved. X2 dash will be preserved, and here we will make an equivalent circuit, that is RE and JX. That is RE equivalent, JX equivalent. This is what? This is VS Thevenin. That means the voltage that is seen here. Open circuiting, after open circuiting, this is VS Thevenin. I'm looking at it. What is the equivalent? This is actually Thevenin equivalent circuit. This is basically Thevenin. This is the Thevenin impedance. This is the Thevenin impedance. That means here we'll say that V S Thevenin is equal to what? It is the open circuit voltage. So open circuit voltage will be how much? JXM by R1 plus JX1 plus JXM into VS. This is the V Thevenin. It will not be very different from VS, I tell you. Sometimes you will see that it will look cumbersome only to get some very small difference in the magnitude and phase with respect to VS. Obviously, because this resistance, this series resistance is very small and JXM is much higher. Magnitude wise, JXM is very much higher. Magnitude of XM is very much higher than square root of R1 square plus X1 square. It is very much normally very much equal. So it almost becomes nearly equal to it is VS. Okay, and other one is the Thevenin impedance. That means Z Thevenin is equal to RE plus JXE is equal to R1 plus JX1 in parallel with JXM. Okay, there will be some change, little change in these values, but this is the actual analysis method, actual equivalent circuit, However, people sometimes make some simplification. What simplification they do in these cases is that they ignore JXM. Assume that JXM is reasonably high compared to R1 and JX1. So if that is assumed, then the equivalent circuit is simpler. R1, JX1, JX2 dash, and R2 dash. They are ignoring this part, assuming XM is very high. This is VR. So this is somewhat easy to solve. So then the current I2 dash square, I2 dash. Let me first write this thing without approximation. So without approximation, it is equal to VS Thevenin without approximation divided by RE plus R2 dash by S square plus XE plus X2 dash square root. So this is what is without approximation, and with nearly equal to VS divided by square root of R1 plus R2 dash by S square plus X1 plus X2 dash square. Right? This is bit approximated. This is the more accurate expression of the current. Right? So based on the problem, if they give you the value of XM explicitly, it is better to solve accurately this method. It is better to solve accurately by this method. Otherwise, you can, if the XM value, sometimes they will say ignore it for simplicity, then you solve it by this method. Okay. Various other approximations also we can do it. Maybe even this approximation sometime will be okay. That is, if S is very nearly equal to 0, is nearly equal to 0, then you can say that this is equal to Vs divided by S into R2 dash, because this part because this part will be dominating over this part, as well as it will be dominating over this part, magnitude wise. It will be dominating over this part. So this becomes much more than R2 dash by S, very much greater than R1, also greater than X1 plus X2 dash, magnitude wise, this one. So so this is the simplest way of looking at the current when the then it is very close to the slip is very nearly equal to 0. Okay, so that is how you calculate the current when it is, and you can see that when slip is very nearly equal to 0, the current is reasonably less. That's why we said that in the beginning, in the starting part of the thing, when slip is equal to 1, current will be more, but as the operating condition improves and it comes to the rated condition, the circuit is becoming, and also you can see that now clearly I2 and Vs are in phase because it is just a resistive circuit. The simplest form, this is just a resistive circuit. This implies that, as I used to tell you earlier, that power factor is good, power factor is nearly equal to 1, which implies that the delta angle is equal to 90 degree, almost 90 degree. But this happens when it is operating at the under very close to the rated condition. Okay. Okay. So by putting this value of current, we can write the torque expression as this. Torque, electromagnetic torque is equal to, you remember that it is nothing but, it was nothing but PG by omega sin, and that is now equal to 1 by omega sin into 3 into I square. We have to write I square. So it is V S Thevenin square into R2 dash by S, and current expression I'm writing from here, that is nothing but RE plus R2 dash by S square plus XC plus X2 dash square. This is whole into a bracket, right? This part is I square. This part is I square. I square R2 dash, 3 is for 3 phase divided by omega sin. This is the actual torque expression. You have to find out, in order to do it very accurately, you have to find out the Thevenin voltage. It is not the stator voltage but the Thevenin voltage, and RE and XC. So you have to find out Vs Thevenin first, then find RE and XC, and then find TE. Before that, you have to find out what is the synchronous speed. All those things, if you calculate, you will get the torque. So it is, you can see that this is a function, is a very nonlinear function. The torque is a nonlinear function of what? Nonlinear function of the slip. So let us plot this one more time. This nonlinear function of the slip, how does it look like? It looks like, this nonlinear function looks like right. So this is torque. This is torque, and this is mechanical speed. So mechanical speed's well identifying point is this point speed is equal to 0. Okay, this is, I am writing omega rotor. This point is omega sin. Okay, but speed can be even more. Rotor speed can go more. So this is generating zone. How do we define? Slip is less than 0. This is the generating zone. Slip is less than 0. Okay, torque is negative. Other way, in other words, torque is less than 0. Slip is less than 0. That means what it means? Omega rotor is greater than omega synchronous. And there is a beautiful symmetry here. There is a beautiful symmetry in this zone and this zone. There is a beautiful symmetry. This characteristics is similar. This speed you can call it 2 omega sin. After that, here you call it 2 omega sin. 2 times the omega sin. This is the I might not have drawn very symmetrically. Okay. So I erase this. Okay. So obviously the speed is 0. This torque is called starting torque. Start. Obviously this is maximum. This is called break. This is called sometimes some names are that breakout torque or maximum torque. Let me call it peak maximum torque. Maximum torque. Sometimes they call pull out torque, etc. Pull out torque means it will pull out. It cannot go beyond that. So that kind of thing. So okay. So this is the intrinsic characteristics of torque generation of the machine. Intrinsically, it is generating. The rotor speed you are increasing. You have given a stator supply. Based on the stator supply, the synchronous speed is developed. The magnetic field is rotating at a certain speed, and rotor speed can vary. So depending upon the variation, we are putting this variation with the characteristics of slip. So this is called slip is equal to 1, and this is called slip is equal to 0. This zone is slip is equal to -1. Slip is equal to -1. This is equal to slip is equal to 2. Right? So this is the way the complete torque speed characteristics of it all comes from that equation. I'm not doing anything. I'm not imagining. I'm just plotting. This characteristics is non-linear. So therefore we are plotting in this way. This has variation. It depends upon this thing. It has a variation. You have to just put the value of slip and calculate. You will get this characteristic. This characteristic. This is the torque speed characteristics of the induction machine with a constant voltage supply. So if you observe a little bit minutely, this zone torque is positive, generator zone torque is negative because slip is negative. Okay, so so what does it mean? Slip is equal to 2. What does it mean? Slip definition is omega sin minus omega rotor by omega sin. So if it is 2, that means 2 omega sin must be equal to omega sin minus omega rotor. So omega rotor must be minus omega sin. That means this zone is possible if the rotor rotates in the reverse direction. Rotor rotation is the reverse direction with respect to the synchronous this speed direction. Rotor is not rotor. If the rotor is rotating, if the synchronous magnetic field is rotating in the clockwise direction, I'm not drawing here. You may get confused. So this zone, if the rotor is clockwise, this is anti-clockwise. Omega sin, omega rotor. This is anti-clockwise. Here in this zone, both of them are in the same direction. If it is this, it is also this. Omega sin, omega rotor, but omega rotor is less than omega sin. Here omega rotor and they are in the same direction, but the speed is different. This is this zone. This is omega rotor is greater than omega sin. That is what is and it is possible when there is a prime mover. Now the energy will be coming from the mechanical side to the electrical side. This is mechanical fellow will be pushing the energy or power, and the electrical fellow will be acting like a generator and pushing that thing to the some electrical load. The power will be giving to the electrical load is now electrical nature, because the prime mover or some mechanical turbine etc. is giving the power and rotating the rotor, right?
Sir, you're talking about the S greater than 1 region, right?
Which one? This is S greater than 1. This region is S greater than 1. This region is S less than 1, negative. Numerically that is again exactly identical to the motoring mode, but it is negative. That means rotor speed is more than the synchronous speed.
So the direction should be same, na? Means if slip is negative, then the direction of rotor and
yeah. I'm sorry, I brought it wrongly. It is in the same direction, but thank you very much. But in the more speed, this is same direction.
Sir, means if rotor is moving in the same direction as the synchronous speed, then how is it generator? Means in generator, the direction of rotation should be opposite to the electromagnetic torque, no?
Now the electromagnetic torque is in the same direction as the rotor direction, but the torque produced by the machine, you see, it is negative. That means it is going the other direction. So let me do it clean job. So when in the motoring mode, this is the torque, electromagnetic torque. This is the load torque. Load torque means mechanical torque. Right? Now this is the, I may say this is the same thing. This is the, because rotation, this is the load torque, and electrical torque is this is the load torque as well as the direction of rotation. So here I'll do it one more time, otherwise confused. This generic thing is, whatever direction electromagnetic torque is there, the rotation also in the same direction. That means omega rotor in the same direction. In the other way around, and you see the mechanical load torque is opposing the direction of rotation, whereas the mechanical torque and the direction rotation will be in the same direction. Electrical torque produced in the reverse direction. So in this in this zone, in the generator zone, if I'm drawing it again, you cut it. Let us say this is the direction of rotation. Let us say this is omega rotor. The mechanical torque is now in this direction, T mech, and electrical torque is in direction, E. This is known as the generator.
So it means the electromagnetic torque will always be in such a direction that it will try to make the slip zero, na? Means electromagnetic torque.
Slip zero depends upon the operating point. Slip zero or not, it depends upon the operating point. What is the load? How much is the mechanical power? If you want to generate this amount of mechanical power, you will be operating here. As electromagnetic torque was there, it was operating here. It will be operating here. That means your mechanical speed will be slightly higher than the synchronous speed.
Means I'm trying to say that the electromagnetic torque will be in such a direction that it will try to oppose the relative motion between the rotor and the synchronous speed, na? Means
did I ever say in these terms? Did I talk in these terms? I didn't talk in this kind of way. I kept it much simple. To me, torque is flux into current. If the flux is same, current MMF direction reverses, then it is a torque reversal. To me, it is as simple. That is electromagnetic torque. So here what is happening is that in the equivalent circuit, current is reversing. In the generator mode, in the motoring mode, actual current flows in this direction in the rotor. In the generating mode, actual current flows in this direction. Actual current flows in the this direction. So therefore, there is a torque which is in the reverse direction. It is trying to stop the machine. Mechanical fellow is driving the machine. Okay, mechanical fellow is driving. Electrical fellow is trying to stop the machine. Stop the direction of rotation. It is going against the direction of rotation. Whereas in the when it is in the motoring mode, electrical torque is applied in the direction where the motion is happening. Electrical machine is the electrical torque is the stronger fellow, bully. It is the bully. It is dictating the direction of motion. Mechanical fellow is opposing it. But at steady state, these two are balanced. Okay. So its direction is reverse. Otherwise, things become uncontrolled. Okay, J d omega by dt has to be 0. Newton's law that eventually the force or torque has to be 0 to reach a steady state speed. Only thing is that in a motoring mode, electrical fellow is the bully, so it is dictating the direction of rotation. In the generator mode, mechanical fellow is the bully. It is deciding the direction of rotation. Its direction and the direction of rotation of the rotor are same, and the electrical fellow opposes that. Electrical fellow is so electrical and mechanical torques are always opposing each other. Has to oppose each other. Otherwise, they do not sum up to be 0. So, so this is the point I am trying to bring to you. Okay.
Yes, sir.
Okay. So with this, just 1 minute. I will take 1 minute. You just derive these expressions. This you can derive now. That just take. I will take 1 minute. That is called that when the maximum torque occurs, this condition happens. R2 dash by S max. This is the maximum, the slip at which maximum torque occurs. You will get it from a very simple application of our maximum power transfer theorem. You have studied that in the first year, that maximum power transfer theorem, maximum power, the impedances must be equal. Power transfer theorem. This is the resistance at which maximum power transfer has to happen. So this impedance has to be equal to the rest of the impedances of the circuit. So this is the condition when maximum power transfer happens, and the maximum torque with that value of slip is equal to 1 by omega sin. If you just put it, you will get it T by 2 into V Thevenin square, stator Thevenin square, same expression, R E plus square root of R E square plus x1 xc plus x2 dash square. This is the maximum. You see that in this expression, rotor resistance is not there, not dependent on rotor resistance. In the next class, I will talk a little bit about a few more things about this torque, etc. But this is application of maximum power transfer theorem, and this is the expression of the maximum torque. And the slip at which it happens is this. This is the slip at which this will be happening. Okay, then I will stop now here. So in the next class, we have some more things to talk about. Thank you very much for listening.
Sir?
Yes. Yes,
So, where will you upload these notes after the class? Like,
it is there already in this, no? You cannot take it from there. download? It is there in the general and the meeting. Can you not take it from there?
Okay, sir, I will check it once.